Okay, so here you are. And you see everybody, right?
I do. Hello. And
Cool.
I should say good evening. Here it's morning.
Yeah. Okay, so I have your presentation here on the ready. Okay, so I guess we don't really need any introductions and we can just start, right? Herb Sutter, convener of the C++ working group. Okay, Herb, I'm gonna switch to Russian, okay?
Absolutely. And
Okay,
I
cool.
apologize that I'll be sticking mostly to English.
Cool.
But
That's easy.
let me just say thank you for inviting me to speak to your group. And I can say at least большое спасибо.
Well, we are very happy to have you here. I'm struggling to put it into words. Anyway, switching to Russian. Это очень сложно, кстати, переключаться туда и обратно. Всем привет, спасибо, что пришли. Сегодня у нас Герб Саттер, главный в комитете по стандартизации, который любезно согласился рассказать нам про оператор Spaceship и поотвечать на вопросы. План встречи примерно такой. Слушаем РБ, задаем вопросы. Потом у нас небольшой перерыв на поесть, пообщаться, минут 10. Потом я рассказываю, что мы делали в комитете. И потом у нас социализация. Ну и, наверное, я тоже могу на какие-то вопросы ответить. А потом социализация. Вот. Все, начинаем. Okay, Herb, your turn.
All right. Well, thank you again. And for most of this hour, I'd like to have quite a bit of time left over at the end for questions and answers about this topic or other topics. But I thought I would start with a presentation about a feature I've been working on that actually just got adopted a few weeks ago, earlier this month, for draft C++20. So we're very happy about that. And I thought I would give you, with the exception of the first couple of slides, I would give you the presentation as I gave it earlier this year to the Standards Committee to give you an insight not just on the proposal itself, but also on the ways that we think about the way that we design proposals, the way that we look at alternatives and decide to move forward on some while leaving other parts for later discussion because they don't have consensus yet. And the core of this has now been adopted, and I'll talk about the optional parts that might come later or might not. So the idea is, I added these few slides to the beginning of the committee discussion to start off with an example. Let's say you wanted to write a case-insensitive string type, CI string, and you wanted it to support all the comparisons between two CI strings and also with, say, char star. C-style strings. And for the char star strings, of course, you want to allow comparison in both directions. So char star compared to a CI string and a CI string compared to a char star. So my question for you is, if you have to write the class like this, let's just say it's wrapping a string under the covers, how many functions do you have to write to get all 6 comparisons between two CI strings and between CI string and const char star both ways? And notice you have to write the ones for char star. I'm not going to let you be inefficient and just convert a char star string to a CI string. So anybody want to speak up? How many functions do you have to write?
Well, somebody said 8, over 10.
18, yes. Whoever said 18, you are right. Here is one way to do it. And this is one of the reasons that people say C++ is hard. And you can't really blame them. Now, in this case, there are different ways you could write this, but you need to write these 18 functions. The first set is between CI string, the second set between CI string on the left and char star on the right, and then the third set with that reversed. And in each case, you'll notice that I'm writing equals and less than in terms of some other case-insensitive comparison function I happen to have lying around. And then the next four, not equals, greater, greater equal, less equal, I write in terms of equality and less than. And that actually creates a needless inefficiency that I'll talk about, but we don't actually need to do that. One of the things about it, though, is when we write these by hand today, quite often this is what we do, is we write the others in terms of equal and less than, just to reduce the boilerplate. Otherwise, there would be even more red on the screen. So with that in mind, here is what you can write now. Here in this slide, it says proposed, but as of 3 weeks ago, this is now something that's in draft C++ 20. There is a new operator that I'll describe in a moment that is less than, equal, or greater than. And so that's all one token. And because it's often called, it looks like a spaceship, like a UFO or a TIE fighter, it's often called the spaceship operator in other languages. And so that's what it's likely to be called again here. And the most important thing is I had to write only two functions, and I get all of the comparisons, those 18 I just showed you, not as actual functions, but as rewrites. So if the user writes a less than b and there isn't a less than, it will look for a spaceship operator and see if it can invoke that instead. And I'll describe how that works in a moment. You'll also notice that it returns not, say, bool or int, but it returns a weak ordering. And I'll talk more about that in a moment as well, because we can actually say what kind of ordering or equality we're returning in ways we can't distinguish from the operators alone. Because, for example, strings, case-sensitive strings, you can compare with all the same 6 operators, equal, less than, etc., but they have a strong ordering, whereas these ones have a weak ordering because two strings may be different, but distinguishably different, but compare equal for the purpose of this ordering, even though one may have a different case than the other. And we can actually say that here, that we are returning a weak ordering. So let me show you how that works and how in this case, just saying weak ordering says generate all the other 6. It's efficient and single pass. It's symmetric. So you'll notice that second one, the operator that takes const char star, is actually generating 12 functions, or the effect of 12 functions. And I'll show you how that works. So first, a lot of acknowledgements. One of the reasons I got involved in this proposal is because coming up to C++ 17's release, quite a few different authors on the left-hand side had tried to bring forward proposals for improving comparisons. One of them, by Bjarne Strustrup, almost succeeded, and at the very last minute did not succeed in getting consensus in the committee for C++ 17. And there were some various technical reasons for that. And so this proposal builds on those and says, hey, if we don't have the time constraint of jamming it into C++ 17, can we step back and do a really elegant job of this? And I want to thank all the reviewers on the right-hand side as well for reviews of drafts of the paper. That helped the paper very much. So there's a core design I'm going to talk about, and then there are a couple of optional parts, none of which actually have been adopted. The core design has been adopted, and I'll distinguish that, and that's 90% of the proposal, and all the interesting parts that I actually care about. The goal is to be complete, correct, efficient, and teachable. Complete so that we can address all the comparisons, not just equals, but also less than, and even three-way comparison, which we already have with strcomp, but we didn't have with the operators. And also be able to address the comparison categories, distinguish strong and weak and partial order, things like that. A cornerstone of this design for correctness is anytime you ask for a default comparison, we do exactly the same thing as copying. So in previous designs, including the one that failed for C++ 17, it's sort of made guesses or approximations based on, well, if it's a mutable member, maybe you didn't want to compare that. And if it's a virtual base class, maybe you didn't want to compare that, which actually made it not consistent with copying. So if you get the generated copy constructor, for example, it copies all the members, including the mutable ones. In this design, I said, look, let's not try to invent new rules. If you can copy it, you can compare it. So default comparison should always have exactly the same semantics as default copying, so that if I say A equals B, so assign B to A, using the default copy assignment operator, I should then be able to assert A double equals B, and assuming that's the default comparison that's being generated. And that way really, I think, got rid of a lot of the questions about, well, were these heuristics and approximations and special rules correct? Because we know we're doing it right, because we're doing exactly what copying does. It's efficient because it's always single pass, and I'll explain that with an example. And it's teachable because we don't have to teach people the boilerplate. We can say one function and we get anywhere from 2 to 12 comparisons, depending on what kind of comparison was requested. So there's two different terms in the paper, and the committee largely stuck with these. So when I say generated, I'm going to try to be consistent. Sometimes I'm use the wrong word, but I'll try to be consistent and say generated when it's something the user didn't declare, like I'm using less than, but the user didn't declare it. I'm just generating it and making it available and rewriting it to the Spaceship operator. And defaulted means you get the default semantics. I've written equals default somewhere. So here's what we teach. This is what I'm going to show you a lot more detail, but this is what we should teach users to do 99% of the time. And pardon the Millennium Falcon, it's just very important to have the right kind of spaceship on the screen for this discussion. So the good way, the way that we teach people by default to write is, hey, look, we have a three-way comparison operator now. If you want for your class X to enable all comparisons, all possible comparisons with type Y, with member-wise semantics, write auto member operator spaceship that takes a Y and make it equals default. And when you say auto, we'll deduce the comparison category for you, and equals default means that we'll do member-wise comparisons. But sometimes you'll want to open the hood and take control. And even then, it doesn't get too much more difficult because you still write just one function. Here's the advanced one with the dark side. We still just teach that the spaceship operator, here's the operator that is three-way comparison. To enable all comparisons of your class X with objects of type Y, write the member spaceship operator that takes a Y. For its return type, return an underscore or so something underscore ordering if you want less than and all the relational ones as well. Otherwise, underscore equality if all you want is equals, not equals. And make the prefix be strong if X and Y being equal means there's no observable difference, like for a case-sensitive string. Otherwise, weak, like for a case-insensitive string where I can have capital A and small a compare equals, but I could pass that to a function and the function might do something different with a capital A and a small a, even though they compare equals, their values are distinguishable. That's what a weak ordering or a weak equality expresses. And I put that just in the return type. And so just by saying one word in the return type, I express all those things. Oh, and then for the body of the function, you can write your own function body, but if you like just member-wise semantics, then you can just write equals default. Now, to put that middle part of the slide in a table form, so we write one function, get up to 12 comparisons. Here is the same rule as the middle of the previous slide in table form. So we tell people, write a spaceship operator. On the right-hand column, if you want less than comparison, return an ordering. Otherwise, return equality if you just want equals, not equals. And on the bottom row, does A equal B imply there's no observable difference between A and B, like for a case-sensitive string? If the answer is yes, return an ordering or equality with the strong prefix. Otherwise, return one with the weak prefix. And that idea of does A equal B imply no observable difference is, we often will talk about it, including in this paper, as substitutability. So if A equals B, is the value A always substitutable for B and indistinguishable? That's what that's capturing. So those are the main four that you would use. Those are standard library types now: strong ordering, weak ordering, strong equality, weak equality. And there's also a fifth one that we added to the standard, partial ordering, which additionally permits unordered results. So it's like weak ordering, but it permits unordered results. So it's possible, for example, to have A spaceship B return unordered, which means all comparisons return false. All of the 6 two-way comparisons return false because there's just no way to order it. It's not less than, it's not equal, it's not greater than, it's none of those things. Which, by the way, comes up with floating point numbers. That's one reason we did that, is so when we added it to the standard, added spaceship also to the built-in types for floating point operator spaceship, which now exists as a built-in function for floating point types, it returns a partial ordering, which is logically correct. Now, on this slide for symmetry and also heterogeneity, we had the example of case-insensitive strings where if you want to compare it to a char star, remember we had to write the comparison both ways, char star CI string and CI string char star, just in case people might pass us parameters or arguments in either order, and we want that still to work. If I can say A less than XYZZY, I should be able to say XYZZY less than A or greater than A and get the same answer. So what happens in the language now is that if I write, say, X less than Y or X greater than Y, so whatever that operator is, that two-way operator, we'll replace that with the at sign for now. So at just stands for one of the two-way operators, equals, less than, one of those. When you write that, if the user didn't write their own, then we're going to look. So first we're going to look at if the actual operator, so X, if it's X less than Y, we'll look for, is there an operator less than XY? Just like today, that's the first sub-bullet. If it doesn't find that, it will also look for X spaceship Y and Y spaceship X. Now this is interesting because this is where you get the symmetry. So that's why when I can write a single spaceship operator that takes a CI string and a char star, and it will find it even if I pass a char star and a CI string, because the third sub-bullet will fire, because I look for the spaceship operator symmetrically both ways. And now here's a subtlety. It's very elegant, but a subtlety. The thing that the spaceship Y returns, so the spaceship operator returns a comparison category type, like strong ordering. The only thing you do with that is compare it against 0. If it's less than 0, then X is less than Y. If it's greater than 0, X is greater than Y. If it's equal 0, X is equal to Y. And the same for not equals, less than equals, and greater than equals. Which means, and this is the cool part, I can rewrite X at Y to just be X spaceship Y at 0. So for example, if at is less than, so I'm trying to compute X less than Y, and I don't have a less than operator, I'll try the spaceship operator and I will simply rewrite X less than Y to X spaceship Y less than 0. And if it was X equal Y, I would simply write it to X spaceship Y equal 0. And the third sub-bullet will do the same thing if I have to flip the order of the arguments. When X and Y are the same type, this covers symmetric conversions on each argument. So like, for example, if I'm invoking an operator spaceship that takes 2 X's and I can convert the Y object to an X, fine, I can invoke that and I just do the conversion, but I get the conversion on either side. If I do X and Y or Y and X, I get conversions on both arguments, just like I would today if I wrote it as a non-member. And when X and Y are different types, like CI string and const char star, this covers symmetric heterogeneous comparisons, and also still allowing conversions if there are any. So this lets me have the power of writing a single operator that is symmetric, that may be heterogeneous just depending on the type that I take, and that I just teach people, write it as a member. There is almost no reason. I'll give one counterexample later, but usually you will never think of writing these as a non-member the way we have to remember to write our comparison operators today. I'll come up again with that in a pitfall section. So here's a simple example. Let's say I have a class name that has two strings, a last name and a first name. And you'll notice that the last name comes first in the class. And what I want to write is on the left-hand side in C++17, I have to write all the non-comparison functions. So for example, after all the non-comparison functions, I have to write all the comparison functions. And I have to write them as friend, bool, operator, whatever, nameref, nameref. And then I write equals and less than, and then for convenience, I write the other four in terms of equal and less than. What this means is I'm actually doing an inefficient comparison. For example, if you look at the highlighted part on the left-hand side, I have to say, is A dot last less than B dot last, or A dot last equals B dot last, and A dot first is less than B dot first. If you look at the A dot last less than B dot last and the A dot last equals B dot last, if there is a common prefix, it has to be traversed twice. So if whatever the common prefix is of string last rather, I have to traverse that twice, once to compute less than and once to compute equals. Whereas on the right-hand side, the proposal is Spaceship is always single pass. I just have to go until I find the first non-equal character, and then I remember whether it's less than, equal, or greater from that single pass, because I've already looked at the information. I don't need to look at it again. I return that, and then I directly rewrite operator less than to Spaceship less than 0. And I don't have to do this two-pass comparison, which is kind of nice. Also, there's less typing. So because I said auto, it says compute the strongest ordering that you can, which in this case is strong ordering, because both string first and string last have strong ordering. So the total comparison can be a strong ordering. So auto will deduce to strong ordering, which means that user code can use all 6 of the two-way comparisons and they get rewritten. And it's, as I said, efficient. It's single pass. We're C++ programmers. We like efficiency. It's symmetric, including I get conversions if I have two things I'm comparing, one of which is a name and one which is convertible to a name. That works whether I pass it as the first or the convertible thing as the first or the second argument. And I'm documenting that I have a total order because I'm inferring a strong ordering, not a weak ordering. Oh, and I get member-wise semantics because I wrote equals default, so I compare one member after the other. So the screen is what we teach people to write. The little bullet, the little post-it note, gives us the details about why it's correct, why it's efficient, and usable, symmetric, and has consistency. Usually, we teach people write Spaceship as a member function, just like I showed there on the right-hand side. We don't have to go and write it as a non-member function like on the left-hand side like we do today in order to get conversions on each argument. Only if you want to get conversions on both arguments at the same call site, you can still make it a non-member. I'll come back to that detail because it's almost always the wrong thing to do. You almost always don't want to make it a non-member because what we have to write today on the left-hand side to make it a non-member actually creates a pitfall. Sneak preview, the pitfall is that on the left-hand side today, I have to write them as a non-member so I get conversions symmetrically on either argument, either parameter. However, that also allows me to use these comparison functions on the left-hand side to compare two things that are neither of which are names, where I'm converting both, and that's almost always not what you want. So we'll come back to that. Here's the example we already saw. How do I do a case-insensitive string? I get to write all these fun functions, and yes, I can do that, and it's cut and paste boilerplate, but then I'd make mistakes with cut and paste, and it's just annoying, and it gives C++ a bad name. I would much rather just write this. And as of 3 weeks ago, I can in fact write this in C++20, and I expect that compilers we'll be supporting this over the next 6 months or so already, because all three major compilers are tracking the standard very closely. So this is actually not very far from actually being a reality that you will be able to use if you're able to use the latest versions of shipping compilers. So this is something in the reasonably near future. And since that small font, just to be able to show these back and forth, I made the font the small. But since now we have all this room, let's go back to a bigger font because we don't have to write so much. And here again, as I said with the case-insensitive string, I'm documenting, notice I'm returning a weak ordering, which still means I generate less than, greater than, equals, and all the others. But I'm documenting I have a weak order where two values might compare equal, but be distinguishable by a function, just like lowercase a, capital A. And I still get symmetric conversions and efficient single-pass semantics. So here, if I write it as a member function as shown, I get the symmetric CI string to convertible to CI string and convertible to CI string comparisons, but not comparing two other types that both happen to be convertible to CI string. If you really, really wanted that, then you could make it a member, a non-member, a friend. So let's talk about pitfalls today. There are three major pitfalls with comparisons the way we do them today. The first is what is known as the stircomp pitfall. And I give credit especially to Gabriel Dos Reis for pointing this out, and he's the one who named it the stircomp pitfall. If I write, because stircomp returns a comparison between A and B. If I could see you, I would ask, actually, I can see you. Let me look at your video. By show of hands, could you raise your hands if you have ever known anybody else, let's say somebody else, to write by mistake if stircomp A comma B when you intended to test for equality? Oh, I see quite a few hands. Yeah, that's so easy to do. And it actually compiles, but it does the wrong thing because stircomp returns 0 if they're equal, which also happens to test false. And then we have to go and fix our code. We hopefully catch that in unit testing. It is for this reason that the spaceship operator return type always has to be explicitly compared to 0. And you almost never actually invoke the spaceship operator directly in user code. But if you do, such as when writing your own spaceship operator that uses other spaceships, you always have to compare explicitly against 0 so that you won't make this mistake by accident. So it is deliberate that, say, strong ordering does not convert to bool and is not implicitly compared to 0. It has to be explicitly compared to 0. The second pitfall is that when you look at the member function, stir operator equal, if I write that as a member function, which is nice and convenient, it means I can compare a string and a const char star string like s equal x, y, z, z, y, but not the reverse. Well, that's a pitfall. So we teach people, oh, well, don't do that. Make it a non-member. But that introduces a new pitfall that's subtler. And that's the third one on the screen, which I referred to earlier. If I do make it a non-member, now comparing x to non-x works, and comparing non-x to x works. If they're necessary, we convert. However, it also allows comparing two completely unrelated types, both of which happen to convert to x. And then this helpfully fires for you, which may not be what you want. But this is unavoidable if today you write it as a non-member friend in order to get the first two lines to work. The third one comes along whether you want it or not. Now we can distinguish between those two. So now if we look at the way that we will resolve those pitfalls, we have no implicit bool pitfall because you can't just say if A spaceship B. You have to explicitly compare against 0, and that reminds you, hey, I'm comparing against 0, so you don't make the implicit equality mistake. We avoid the default asymmetric pitfall because if you write a member function, you get symmetry. And we avoid the unrelated comparison pitfalls because only if you really wanted to compare two things that are convertible to x, neither of which is x, only then would you make this a non-member function and write it as a non-member yourself. So you can still get that behavior if you want. It's just not the default. So I'm getting the good symmetry without the baggage that I have to get today because I can't distinguish those cases with the tools I have today. So that is the proposal that has come into C++20. We have also introduced the Spaceship operator for built-in types, including pointers, floats, integers, bools, chars, and that kind of thing, and arrays. We're also now in the process of also adding Spaceship for standard library types. So those are not yet in C++20, but David Stone and others are writing papers now to apply the Spaceship operator to the standard library so that std string, std vector, all those will get Spaceship operators as well. And one of the interesting questions is that the library working group is looking at, and that I mentioned in my paper 515, is once you have the Spaceship operator, one of the choices you can make is to remove the existing operators. And it turns out that the standard library might or might not do that, because if you remove the existing operator, you could break code that takes the address of it and assumes it's a real function, because if you replace them with Spaceship, you can still say A less than B, but less than isn't a real function, it's just a rewrite. We're not proliferating functions. So I assumed that the standard library would want to maintain compatibility and say, oh, well, because somebody might be taking the address of string less than, we have to just add Spaceship, but we can't remove the others. It turns out the library says, user code shouldn't be taking the address of that. We already told them not to do that. We might not care about breaking such code. So it's actually possible that thanks to the Spaceship operator, that the standard library gets several pages shorter, because if they do add Spaceship and remove 6 or 12 other operators, the standard library specification might save itself a few pages, maybe even a dozen or two pages, which is not bad, because we're always adding pages to the standard. It would be nice to take some away. There are also in the paper some comparison functions and algorithms that you can look at. I'm not covering here. For instance, types that naturally have a partial order, like floating point types, there is a way to actually ask for a strong ordering. So std strong underscore ordering, or strong order rather, lets you ask for a strong ordering that might be more expensive to compute than the usual ordering, and therefore it's not the default for the operators, but it's available if you want it. So IEEE has specified a strong ordering for floating point types, which is more expensive to compute. You can get at that with the std strong order function rather than with the operators, which return partial ordering. Now, there were a couple of optional things the committee did not go for. One of them was if you did not write any comparisons yourself, not even Spaceship, should we helpfully generate comparisons for you? So in this example, option 1 is what the proposal as accepted says. I write my own one-line operator Spaceship. But option 2, which was proposed, and I know Bjarne Strustrup in particular wanted very much, is that no, you just don't have to write anything. You just get the same effect as option 1 by default. The committee has not yet been convinced that this is a good idea. I think they're wrong, but I also think it's not important. As the major benefit is to get from the left-hand side to option 1. If we can additionally convince the committee in the future to go from option 1 to option 2, so much the better. In a nutshell, people are concerned that existing types, like for instance the C time T type for timestamps, it might confuse people if suddenly those become comparable, which they aren't today. And my position and Bjarne Strupstrup's position on that is that's strictly better than today. It just lets you do strictly more than you can do. It makes C++ a better C than C. I can use time T as a key in my set type, for example, and it does no harm. It doesn't matter if the comparison has any comparison to something in the real world. It is a comparison, and I can use that. For some reason, people are squeamish about that, so I deliberately structured the proposal to make that an optional part so that we could get at least option 1 through and then argue later about option 2. So we'll be arguing later about option 2 because I know Bjarne still wants that. The other part that is optional and was really experimental, and I was pretty sure was going to be rejected, but it's always good to have a proposal that has something, a sacrificial lamb that gives people a chance to reject something so they feel like they've done something. Did I say that out loud? Is chaining. So the idea here is sometimes we write, if you look at the bottom example, sometimes we write if A less than B less than C. And we've probably all written that by accident. And of course, that doesn't compile except by accident if what actually usually does the wrong thing. If A less than B returns something that happens to be comparable with less than to C. Whereas really what we wanted A less than B less than C to mean was if A is less than B and B is less than C without evaluating B twice. So the proposal, in short, included doing that, which also enables fold expressions to work, as shown at the top. But the committee decided that was too experimental and didn't want to do that yet. And so that part of the proposal, which was deliberately designed to be optional, was also not yet approved. So we have the core part of the proposal, but not the comparisons if you didn't write anything at all or the chaining. So I asked for these 3 polls from the committee. The first one succeeded. The second one went for option 1, which is do nothing, and chaining was rejected, or shall we say, deferred to a future meeting. And so now we have operator Spaceship. The spaceship has landed, and we have operator Spaceship in C++. So I'm happy to take any questions that you might like. I see hands, but I'll rely on you guys to take the hands and pass the microphones.
Hello.
Yes.
Thank you for your talk. Do you understand correctly that now the member operator Spaceship is the only member which may be called on an object of a different type with implicit conversion? So my question is actually, why is it tied to the name of a method rather than some kind of attribute like implicit or you name it?
So the committee talked about that. And yes, you're completely correct. This is the only type that now can be converted, where you can get the conversions on the left-hand side symmetrically. If we like this idea and want to apply it to other things, then we can provide a more general mechanism. For this proposal, it's hardwired into this specific operator. And it's also because we know the semantics of the operator. It's because it's known to the language. So I could imagine something like what you suggest, and an implicit attribute or something like that allows you to get conversions on this for other reasons. But notice that even if we do that, Spaceship is still special. And the reason it's special is because it has that mathematical property that I can take x at y and convert it mathematically soundly to x spaceship y equals 0 or at 0, or to 0 at y spaceship x, because I can do the symmetry, and the equation is the opposite. That is not generally true of operators. It happens to be specially true of Spaceship. And so because we didn't have enough data points to design the general feature, because you want at least 2 examples before you design something general so you know it's going to be flexible and work, we put it specially into this feature. Now, if in the future we get a more general feature, we can go back and apply that instead, rewrite the wording for this feature to use that general feature. But for now, we've hardwired it specially into Spaceship because of its mathematical properties.
Thank you very much.
Actually, I have a bunch of questions. And first is, you talked about adding a spaceship operator to a standard vector, for example. Mm-hmm. And I have a question. So, will it be...
I think I know what your question is.
Will it be implemented in terms of spaceship operator of a base type or in terms of operator less of those? They could be different if the user redefine them. So what is the answer?
Okay, So I think your question was slightly different than the one that I expected, so I'll try to answer both. I think the question that you asked is, well, what if the operator less for the user defines something for vector of t, t has its own less than operator. Well, vector should already be using that. So the spaceship operator that we define in the standard library for vector, so std vector operator spaceship, should be consistent with what those comparisons less than equals on vector already do. So whatever they already do in terms of the user defined type that it's containing, vector of t, whatever t comparisons already do, that's already covered with the two-way comparisons vector has today. And Spaceship should do exactly the same thing as those.
But that way
now,
it will
before
be...
I answer the question that you didn't ask, did I correctly answer your question, or did I not understand your question?
Your answer means that operator spaceship for a vector should be implemented in terms of operator less of a template type, and that may be inefficient.
So it should be done in terms of operator spaceship on the templated type. Now you're saying, what if it doesn't have a spaceship? That's a very good question. Remember those helper algorithms that I mentioned in the standard library? Strong order, so you can get a strong order even if there isn't a spaceship. One of the fallbacks there is in the strong order function is it will try for a strong order for spaceship if there is one. Otherwise, it will fall back to less than and equals. And so if you look at that part of the paper, P0515, you'll see that there is a fallback there exactly for that case. And so the vector spaceship operator should be written in terms of the strong underscore order function algorithm on T, because it does that fallback, or implement the fallback itself. Mm-hmm. Now, the question you did not ask, but is a really good question too, and it's also about vector, is now for vector, is operator spaceship guaranteed to be maximally efficient? And the answer is yes, but no. Yes, it's guaranteed to be maximally efficient in terms of what I mentioned, the one pass versus two pass. We don't take two passes over the data over the common prefix as we would if we had to revert to fallback to less than or equals. So from that point of view, it's great. It's maximally efficient. However, how do you implement vector of t operator equal equal? What is the most efficient way to implement just equality on two vectors? What's the first thing you look for before comparing any elements at all?
Size.
Size. So first you say, if the two sizes are different, not equal. I'm done. I don't have to look at any elements at all. And that is much more efficient than even Spaceship going through and finding the first non-equal element. The good news is, Spaceship is designed so that if you did not write your own two-way comparison operator, it will fall back to Spaceship. So what we're going to be doing in the standard library, I expect, for vector and string in particular that have a size, or anything that has a constant time size, is provide operator spaceship and equal not equal. Equal not equal will be written to take advantage of that optimization, and all the rest would fall back to spaceship. So that's another, since you mentioned vector, that's another nice detail to know, is you can still overload the two-way operators if you want to do something different, usually more efficient. The cases where that comes up are fairly rare, but they're still useful. And so it's worth knowing about that trick.
Okay.
And it's still better than writing, 18 by hand yourself. You can still write just a much smaller number.
And the second question, you talked about adding spaceship operator to floating point types, and I have a question. So what if operator spaceship for two not numbers returns?
Yes. So as I mentioned, operator spaceship returns a comparison category type. So strong ordering, weak ordering, strong equality, weak equality are the main ones, but there was also, remember, partial ordering. So the ordering suffix means you get all the 6 comparisons, including the less thans, not just the equals. But partial means you additionally get the unordered result. So if you compare two nans, two not a numbers, or a not a number in anything, you will get an unordered result, an unordered return value. So partial ordering has a state that is unordered, and when that maps to any of the two-way comparison operators, it will return false because it's not equal. It's all except for not equals, of course. Not equals returns true, but you can be both not less, not equal, and not greater, and that all of the less than, equal, and greater should return false. And so if you look at floating point types, what we did there is their built-in spaceship operator returns a partial ordering for exactly that reason. Oh, and by the way, even if it wasn't for nans, we would still need to do something special for floating point types, because even if we decided to ignore not a numbers, which I think is not the right thing to do, but even if we did, it still couldn't return a strong ordering. It would have to return at least a weak ordering, because there are at least two values that compare equals, but that are distinguishable to the program, and that's +0 and -0. Gotta love math.
Hi Herb, thank you for the presentation. Do I understand it right that if we rely on auto spaceship equals default, the result of comparison is dependent on the order of the class field? So if, for example, we switch string last and string first in the name, the resulted sorting would be different.
So there's two parts to your question. So the first part is, if we say auto spaceship equals default, is the type of the return dependent on the order? No, but the type of the return is dependent on the strongest common comparison category of all the members, regardless of their order. But the question is the value dependent on the order? Yes, it is member-wise, and so it depends on the declaration order of the members. Just like copying, it follows the exact same behavior as copying.
Thank you.
And if you wanted something else, then you could write your own body instead of equals default. Mm-hmm. That's right.
And the second question is, considering the work in progress concept TS, was there at some point an idea of maybe defining some sort of concept comparable instead of spaceship operator?
So two parts to that. So first of all, it is no longer just the concepts TS. We actually voted that into C++ 20 in July. So that's actually now in the standard C++, the lion's share of it. And for the second part, is there a comparable concept? We deliberately decided not to go that route because concepts wasn't flexible enough and it wasn't powerful enough. In particular, one of the things that it doesn't let us do, it's still just using a concept to say, is something less than comparable or is something equals comparable? You could do that, and there are concepts for that. But that still doesn't let you have a three-way comparison easily. I mean, you could make it a named function and have a convention, but it doesn't let you have a way to have a three-way comparison to get the efficiency benefit, to avoid the two pass on the common prefix in the less than or equal case. And the other reason is because that alone would not let us distinguish the strength of the ordering or equality, whether it's a strong order versus weak order versus partial order, or a strong equality versus weak equality, because a concept can only detect whether structurally it matches a pattern. Structurally, does it have equals and less than? Well, if it has both, then we can say it's an ordering, but we can't say what kind of ordering. We just know it's an ordering because we found a less than. And so concepts is still a very useful feature. It's still very good for type query, but it didn't give us the information that we needed here for this particular use.
Thank you.
Hello, Herb. Thank you for the talk. I wanted to ask you, can we create two or more spaceship operators using one type? For example, to compare two start strings, case sensitive or case insensitive. So we could pick the comparison style, maybe.
So the question is essentially, can you have two spaceship operators that on the same types that do two different comparisons, not in the same namespace? And like you can do that, but then you would have to put them in different namespaces. For the simple reason is that they would have the same signature. The signature does not include the return type, and so you can't overload two functions that have the same signature. If you wanted to do that, you could put them in different namespaces and then just judiciously using the one that you want. You might at that point want to have a named comparison function to make the code more self-documenting, that I'm asking for a case-insensitive or a comparison or a sensitive comparison. Because remember, the way to think about this is the operators are special. Every type you author has a default style of comparison. Whatever that default is, that's what you should make the operators mean. If you want additional things besides the default, you can use named functions or, like I say, namespaces. But the operators want to be like the canonical way to compare objects of this type. If a type has more than one way to compare, generally you want to make one the default and give the other a name that then can be used in the code and is more self-documenting. Or have a different type. Just provide two versions of the type. Each one, maybe they can convert to each other, but each one has its own ordering that it always uses.
Okay, and can we return the ordering type from this named comparison function? For example, to return weak ordering from compare function.
Oh, well, if you have a named function, then you can return whatever ordering that you want and then wire it into whatever algorithm you're using. Sure. But just in general, whether it's a spaceship operator or a regular function, two functions cannot differ just by return value. That's just not allowed in C++. So they would at least have to be put into different namespaces, or better yet, given different names.
Thanks.
So Herb, first of all, thank you very much for a very interesting talk. My name is Vasily, and I have a confession. Never in my life...
That's good for the soul.
Yeah. Never in my life I wrote my own implementation of STL. And as an application developer, I have another confession that the boilerplate code is not of the most or not the worst evil for me. And not even getting the latest tiniest bit of efficiency is the most important for me. And
now you've gotten into heresy, but continue.
Exactly. So disclaimer. I'm still writing in C++. Yeah. So as an application developer, I understand that for STL and for very basic libraries where you do have to get all those little tiny bits of performance, these starships operator are probably something that is needed and something that you are willing to get. But as an application developer who is also trying to work with application problems and also coaching some other developers, should I forget everything what I've just heard, basically, and just use it from std vector and whatever else implementation and just live a happy life?
I always recommend leading a happy life. Nothing in computer science should ever get in the way of that. So I completely empathize with what you're saying. Many of the features that we put in the standard are for type authors, and this is one of them. If you are not writing any of your own types, but you are just using other people's types, you will never notice that they are using the spaceship operator instead. This is good. Will you still benefit? Probably. Your code will be a bit more efficient, which may not matter until the day that it is, and you discover that it's in an inner loop and you can't optimize the comparisons that your library is doing. May never happen, but you'll get that benefit just transparently. It doesn't cost you anything. Another benefit you might get is correctness. Every time that we have to repeat code as a type author, so I'm the type author that gave you the type, so you don't need to know what I did, but keep myself, I might make a mistake. And bugs have been found in these boilerplate functions because I just forgot, I flipped the sign, or I did something wrong, because every time we repeat ourselves, we can get it wrong. But if none of those things apply, then it's no skin off your nose whether the type author had to work a bit harder to write more functions or not. You're right. However, if you ever write a type yourself,
We never know.
things like, oh, you got to make a non-number, and otherwise you won't get conversions on both sides, but you probably didn't do that the first time and you didn't notice till you got a bug report from the field. So primarily, if you're a type author, this makes your life better. Now, having said that, even as a type user, if your type author made the mistake of providing a member comparison operator, and now you realize I can do A compare to less X, Y, Z, Z, Y, but not the reverse, and you grumble and you send them a bug report, you won't have to do that. Furthermore, if they fix that bug, but today you could still write X, Y, Z, Z, Y equals foobar, and you didn't mean to get the other X comparison operator when neither of your objects is actually of type X, you've now eliminated a small but real pitfall in your code as a user. But the best thing of all is we don't have to teach any of that stuff anymore. And I'm all about not having to teach that stuff anymore. Life's too short. There are more interesting things to teach.
So good to know that I still am allowed to be happy.
I strongly recommend it.
Thanks.
Besides, isn't the goal that we can be happy in C++, not by trying to switch to another language and hoping we'll be happy there?
By design.
Yes.
Hello, Herb. I wonder what is behind this ordering types. Is it just a count or just some size t? And I wonder, are we allowed to make our own ordering and put some useful stuff there, and, for example, comparison results and so on?
Yes. So the ordering type, the actual value that it stores, like for instance, a stood strong ordering, is implementation specified. It's up to the implementation. It can be as little as 2 bits, because all we need to store is basically -1, 0, +1, and then for partial ordering, an unordered result. And so we actually leave it up to the implementation whether they want to use an int or a char or what they want to use under the covers. And the main thing is that we have already had the requests from the compiler writers for the standard library implementers to please agree on what they write, because then the compiler writers can make this really efficient. If they know what the layout is going to be for that data, they can make these like really, really efficient. If you want to know how efficient, this is where a group of compiler writers, the core working group 3 weeks ago at the standards meeting, got into a very excited discussion, and of the library implementers too, in the library working group, into a very excited discussion about how they could do this without even a branch. They could do the comparisons without any branches. This is how hard they want to work for you. And so it's very likely that the compiler writers and the standard library implementers will agree, even though it's not specified in the standard, will agree on what the exact layout of these types is, so that the compiler can take advantage of it for you.
Thank you. And can we define our own ordering types?
Oh, that's right. So it is, the proposal deliberately did not go into can you define your own and how would you do that. Nevertheless, we did think about that at the time, and it is largely supported. So right now, if you look at those ordering and equality category types, the way that they are not related by inheritance on purpose, they are related by conversions. So each one has a conversion operator. For instance, strong ordering has a conversion operator to weak ordering and a conversion operator to equality comparison and the others, the weaker ones. And partial ordering has a conversion only to one that's weaker than it, which is the weak ordering, for example. Because of this, they are loosely coupled, and it is possible for you to have your own ordering type that can be returned by a spaceship operator that converts appropriately to those others. Now, there are going to be some situations where you can't, that you won't be able to express with just conversions to those types. But largely that should work, even though it was not we did not explicitly design it from version 1 to make sure that that was fully supported. We also had an eye on that and made sure there was nothing preventing it. And in fact, many of those uses we think actually do work already, even though we're not making a guarantee that all of the uses may work.
Thank you.
But the key is you define your own type and conversions to the appropriate other types if you want to allow weakening, and it should all work.
Thank you.
Any question we didn't ask?
Oh, probably many. Thank you for using the microphone. I can hear you fine.
Okay. So I have actually a question on a side topic, but we don't have you every day here, so I guess it's my chance to ask. So speaking of const expert, which you put a lot of efforts into, when I'm looking at what we're heading at, it seems that like in 10 years we'll have const expert on everything except for I/O operations, and people will stuff more and more.
I'm so sure about I/O.
Things, into headers. So two questions actually. Do you think in heat side probably we should be headed to direction where a compiler should derive automatically whether it sees a definition of a body of a function, whether it's const expert or not? And the second question is, do you think we might have something like link time const expression, which would eliminate the need, blotting our headers with function bodies, and instead many compilers already do the link time optimization. If we manage to add this additional pass to be allowed by the standard in some forms, it would reduce the complexity a lot.
So both of those, maybe. So from the beginning, the designers of const expert, primarily the initial one was Gabriel dos Reis, who I've mentioned before. He has always said from the beginning, the committee wanted to see this const expert keyword, but it's not really necessary because we can infer it. So he's known that from the beginning. Nevertheless, I think it is useful to have const expert explicit, at least in some cases. And if you look at the other talks I've been doing recently about metaclasses and compile time code, the idea of having a const expert region of code that I know is guaranteed to be run at compile time, which does not exist yet in C++, is one of the proposals that are still gestating. I think that's a very useful thing to be able to say and to be explicit about what must be at compile time so I can control that. The second question about link time, that's an interesting direction to explore. I don't know of specific work to explore that. That kind of question would arise naturally, I think, once we have the concept of here's a compile time piece of code in the language.
Okay, thank you.
Hello, Herb. Thank you for your talk. And one more off-top question. You've told about static analysis that finds memory bugs at CPPCon 2015. What's the progress in this direction, and are you going to expand the rule about memory working safety in core guidelines?
Yes. So good question. It has taken embarrassingly long, but the work still continues. And in particular, we are probably within a few months of starting to ship baby steps of that in the checker that Microsoft ships for the guidelines core checking. And that is expected, as it succeeds, to feed into the core guidelines. Notice it's still quite experimental. It will not catch all memory errors. But when you look at memory errors as respects bounds, that's what span is for, that comes from this core guidelines and is coming into the standard. When you look at lifetime errors, leaks and dangling in particular, that's what this one you're asking about is about. So we expect to have implementations in a static analysis of some of those in the coming months. And it'll be baby steps. It'll be because the other thing we're doing is still working on writing a formal static analysis specification of what these lifetime rules would be, so that we can at least within a given function do some analysis if you're using an invalidated iterator, things like that, which is the same problem, in my opinion, as using a dangling pointer if you could see the site of the invalidation locally within the function. People write that kind of mistake all the time. It's one of the reasons we have checked STLs. And I'm still optimistic about that. We're still actively working on it. In fact, as soon as we're done this call, I will be going back to reviewing the latest draft of that spec. That's my job for today. And so, but it's taken longer because there's so many things going on in so little time. We were very busy with shipping C++ 17, but the work on that does continue, and I'm still hopeful it can lead somewhere, but don't expect it to be full memory safety, but we can catch a lot of local uses of invalidated pointers and iterators.
Thank you. We are waiting for it.
Yes, I understand. Thanks for your patience. So am I. Hey, it's one of those things where if you think that, hey, here's a class of errors that we can catch and it's really great, and if it turns out you only catch 1/3 of those, that's still pretty good. So I'm still hopeful for more than that, but we'll see how far we can get in the coming months and a couple of years.
So I guess that's it. Thank
No
you
more
very
questions.
much.
Thank you very much for having me, and enjoy the rest of your evening.
Yeah, so thank you.